you, sir. Hello, everybody. Thank you for that introduction. So I am a senior staff software engineer at LinkedIn here in New York City. And I wanted to sort of talk today about something that might have been useful to me and my team when we were setting out to build this project. So that's kind of the perspective from which I'm going to be talking about. Yes, I am in New York. I live and work in New York. I don't have to travel remotely too often. We have an engineering team of about 40 people now. That's our T-shirt. That's our mascot. And we are hiring. Thanks, Peter. And the project I'm presenting today, it was work of a team. It wasn't just me. So one of the other colleagues, David, he's here in the audience as well. You can bug him later. And it's collaboration between the content ingestion team, which is the team in New York, and the search network analytics team, or the data science team, which is located in Mountain View, but we're getting our own too. One of my other colleagues, Xiao Cheng, is around here, or he's probably on the data science track. So what would motivate us to actually go get data from the web, right? So our dream is to help people more easily navigate the sort of global economy, right? And the idea there is to create an economic graph, sort of a first digital map of global economy, and that will help us kind of help people find opportunities in the world. So what makes up this graph, right? It's member profiles, company profiles, jobs, skills, schools, that kind of stuff, right? And LinkedIn has a lot of this, right? Like we have 400 million members, we have several million profiles for companies, millions of jobs, skills, all that stuff. But there's quite a bit more of all of this stuff out on the internet, right? Like we don't have all of this data. A lot of it is out there. So, how many people here have a LinkedIn profile? Right, so wow, great penetration, excellent. So most people here do, great. How many people here update their LinkedIn profile for reasons other than looking for a job or having just acquired a new job? Yeah, you see, so that's the thing, right? Because there's lots more things that are happening in the world, right? You publish a paper, you present at a conference, that kind of stuff. People tend not to necessarily do that on LinkedIn profile, so we wanted to help with that, right? How many people here work for a company has a page on LinkedIn, like a LinkedIn company page? Right, so that's another thing. How many people here have a job on their company page, but not a job on LinkedIn? Like the job posting on company pages on LinkedIn, right? So these are the kind of things that problems solve. This is what we want to work around. And so we had this big idea, right? Like, of course, we need to crawl the entire web. Of course, we need to get all this stuff in real time. We need to pull it all in, and we need to get it up there as quickly as possible, right? So this is the original big idea. So throw 30,000 QPS of web pages at our, SAMZA cluster. Pump all these messages in there using Kafka. That gives us 2.59 billion pages per day rate, and we would crawl the web, and everything would be great, and then we'd filter out all this stuff nearline using SAMZA, processes that would filter the data down to like a manageable 1,000 pages per second, and that would be like only 86 million new objects per day, and would be great, and we'd be done crawling the entire internet in like 6 months or something. And that was sort of a great idea, and it was inspired, influenced by this paper that talked about potential architecture for extendable web crawler. And the idea of this paper is that you kind of know your queries ahead of time. So we know the companies, we know the people, we know the skills, the jobs. So we have the search queries ahead of time, so you can kind of pre-compute what your search results would be as the data is streaming through. So that's the idea of this paper. And it's kind of it has legs, right? The folks do this kind of stuff for filtering packets as they're coming through the network, so it's viable to do something like this. And then we kind of went to pitch this big idea to other colleagues, and they helped us focus our vision, right? They asked a bunch of questions. Who would use this tool? Do we need to crawl the entire web, right? Given that only so much of it is actually useful to us. Do we need to process pages nearline or like, in a streaming fashion? Do we need, where would we store all this data, right? The internet is big, like really big, lots of data. And how would we correct mistakes in our flow, right? If we were doing this, if we're doing stream processing, right, where the data retention is kind of shorter than if you had it in some permanent storage, how would you correct that system, right? How would you fix mistakes in your model, fix mistakes in your processes? So the who would use this product was answered by the identity team in LinkedIn. This is the team that manages the profile. So your LinkedIn profile and all the different services are related to that. That's managed by the identity team. And it turns out that most value proposition to members, so people who have a LinkedIn account, is related to your profile, right? If your profile is more complete, then it's easier to find you with search queries. So it's easier for opportunities to sort of find you. This is how recruiters would find you on LinkedIn. This is how they would reach out to you. People who you know, right, depends on how full your profile is. All those relationships need to be captured to do that. And sort of establishing yourself as somebody who is a thought leader in the industry, you can display that on your LinkedIn profile. So all kind of central to LinkedIn profile. However, doing this on a mobile device, sort of updating your profile on a mobile device, is a little bit tricky, right? It's kind of tricky doing it on your desktop. Most of you from the audience don't really keep your profile up to date, right? On the mobile phone, that'll be even more challenging because it's hard to enter all this stuff in, right? So the idea that the identity team had is to have a smarter way to build your profile, right? Go out, find content that you would be proud to share in your LinkedIn profile that's part of your professional identity. Bring it to you and say, hey, it looks like you just spoke at this conference, or hey, it looks like you published this paper in the Science Journal or the Nature, right? Add it to your LinkedIn profile, complete your identity. And then sort of you press a button, say, yes, it's me, yes, these are my co-authors, and there you go, it's on your profile, no typing. So that's the kind of use case we were trying to solve for them. So we spoke to them to understand what the use case is. And because Kafka and Samza featured prominently in our initial sort of idea, our design, we went to speak to those teams. And so there was a talk here yesterday on Kafka, and a bunch of people are familiar on Kafka. So who knows what Kafka is? All right. So in general, just an abstraction, it's a distributed commit log, right? It's basically, there's a producer, they create a bunch of messages. There's a consumer that reads the messages from the log. They're kind of decoupled from each other. And that's sort of, in general, very briefly, Kafka. And nobody yesterday didn't seem to know what Samza is. How many people know what Samza is? OK. So I'll briefly describe that as well. So say you have these Kafka consumers and producers, right? And say you want to tie up a bunch of them. So I produce something, then I have a consumer that processes it and produces another event, and so forth, right? You can kind of chain these things together. Now you can do that manually, right? You can set up the producer and consumer, and then you can put in checksums and figure out where you fell over and how to recover, right? So Samza is a framework that lets you make that happen without having to worry about all the different concerns that are involved in doing that. It lets you tie together all these different message queues to produce a result. And also has some local storage too, right, which you need to take care of on your own. And at LinkedIn, Kafka and Samza are supported by an operations team, right? They're responsible for making sure the clusters are up and running, that they're healthy, that there's no lag, there's no delay, all the hard drives are spinning in an optimal way. So we went to talk to them about our use case, right? And it turned out that our use case was not a perfect fit for this. Specifically, the average size of an HTML page, which is the stuff that we'd be sending through here, is about 6K. And according to httparchiver.org, most of them are bigger than that, right? So only 10% are less than 10K, 37% are less than 10K. But generally, the kind of messages you send through Kafka are kind of small messages, right? They're not on this size. And Samza has no problem handling the workload we're going to throw at it, right? We were going to say something like 30 QPS, right, which is nothing. There's experiments that show 1.2 million messages per node per second, right? It's incredibly high throughput, so that wasn't a problem. But the size of the type of data we were throwing was. And the other problem is data retention, right? So SAMSA kind of relies on Hadoop or on Kafka to keep the data, the messages, right? And you can kind of replay from Kafka to repopulate your SAMSA processes. So where would we store all this data, right? That's a lot of pages, a lot of data. That wasn't necessarily a good fit. Then another thing is we didn't really know how we were going to match members, right? So we didn't have a model built yet, and kind of trying to train a model or build a model or without knowing what it is in SAMSA would be challenging. And one of the things that, one of the reasons SAMSA is so fast and performs so well is because it adds some constraints to your implementation. One of the constraints is, it's not like a hard constraint, but it's an advice. The advice that you get is that you don't want to make remote calls to remote databases if you need data on your processor. You want to store that data locally on the same node as you are going to process that data. So what that means is if you want to get data from some external database, you actually copy it, replicate it into your SAMSA cluster, right? So you take your database and you basically replay it as Kafka messages into the SAMSA cluster. It's a viable option, right? Because you can process billions of messages in really short time, right? Or millions of messages in really short time, and you can build up the database, you can go locally. But you still have to do that. That's still a step that you need to do. And once again, if you don't know what part of the data you need, it's kind of hard to do that ahead of time, right? So not a good fit still. So that's bootstrapping it. So we spoke to them, and we spoke to the identity team, and we came up with this project, Satori. Now, Satori is a Japanese Buddhist term. Talks about like awakening or comprehension, understanding, sort of like enlightenment, roughly translated. And what we wanted to do is like sort of enlighten our 400 million members, right? Help them realize their professional identity on LinkedIn. And we were going to find sources of professional content, right? Stuff that you'd be proud to have on your profile from the public internet that's available out there. Grab it, extract it, structure it, and then match it to member profiles, right? That's the idea. So we went ahead and tried to figure out, we as a team, we had expertise in fetching data, right? We operate like a sharing backend here, so you drop a URL, we fetch the data. We knew how to do that. We had some expertise with Hadoop, MapReduce, and we had some folks who had experience with machine learning, but we never put the whole thing together, right? And and it turned out that this kind of problem that we're trying to solve is known as web data extraction, right? For web data extraction, there's lots of different ways to kind of think about how to do it. And there's a great survey paper that documents, Emilia Ferrara, that kind of documents the different techniques and the different ways that web data extraction is used. So you saw an example today, right? The Spotify folks just earlier talked about how they go through blog posts and news posts and they gather data about artists, right? So it's sort of a social use case, social web use case, right? They want to get this information to enrich their own applications. There are enterprise use cases, right? If you want to find out your competitor's pricing, you go scrape their website to find out what competitor's pricing. Not advocating that, but that's just the use case. And they talked about the different use cases, the different sources of data, right? Something that's like intranet versus internet, and bulk data or sort of fetch data. Then they talked about how you would get about getting this data, right? Do you have a full browser? Do you have something that's programmable? Do you have a crawler? Those are different pieces that they talk about. And they also talk about this idea of wrappers, all right? And how different people decided to wrap web pages to get data out of them, right? And they talk about tree similarity using XPaths, specific programming languages for this purpose, or generic programming language that you use to implement this purpose, right? They talked about this. I'm going to dig in a little bit more about wrappers, right? So not candy wrappers, but web wrappers. So that's an example of actually web wrapper implementation. It's just JSON data. And The way they defined web data, in the survey, the way they defined web data wrappers is a procedure that might implement one of many different classes of algorithms which seek to find data required by a human user, extract them from unstructured to semi-structured web resources, and transforming them into structured data, merging and unifying this information for further processing in semi-automated or fully automatic way. Okay, was that helpful? All right, so what it actually is think of it as an inverse function on your template that was used to render the web page, right? So there's some database underneath the covers. There's a template that is filled in with that data. And a wrapper is a way to like remove the template, just get the data back out and store it in your own databases, right? Inverse function on a web page. And it can be, you can implement however, right? You can imagine writing this as a Python script or a Java code or whatever, right, to do it. You can use XPath CSS selectors to get the data out as well, right? But however, or you can just parse the DOM tree, right? But however you're going to do it, you're going to have this problem that you have written some code, some implementation, right? And you did an extraction, but now the page changed. So you have to constantly kind of catch up and make sure that your function is the same function as they're using, or the inverse of the function that they're using on the other end, right? It's kind of a painful process. And it's not a painful process if you're going after like 5 sites or 2 sites or 1 site, but it's a painful process if you're going after thousands or millions of sites, and that's where our aspirations lie. So it's good to get actually some industrial research on this and see what we're doing. And Yahoo Research published a lot of work, and they did a lot of research to figure out how to build this for their scale, right? So they figured out how to induce wrappers from the data, right? So you don't actually write any wrappers yourself. You look at the data and you figure out how you can extract structured data from here, right, in an automated way. They build wrappers that are robust, right? So they actually went ahead and analyzed how data changes over time on the web and how the structure of the web page changes and what parts are likely to be added or removed, right? And then decided that if you build your XPath expression in such a way that you don't include divs for it, for example, you're less likely to break that XPath expression in the future. So that's the work they did. They also figured out how to cluster similar pages based just on the URLs, right? So you're going to build this wrapper. It's going to apply to a particular data source, particular set of pages. You need to figure out what those pages are. So you can both figure out how to build a wrapper on top of it and apply it effectively. And they did one other interesting study. They analyzed the structured data on the internet, and actually turned out that we as users are interested in stuff that's out on the long tail. So the long tail of the data is important. You can get the data from like the top sites, but our interest for information exceeds just the top sites. You really have to go deep, deep into the long tail in order to get information that we are still interested in as users. Now, the reason they were able to do all this great work is because they actually had all this great data, right? They had a crawler. They operated a search engine. And they were able to kind of execute, or do all their research, all their analysis on an existing set of web pages that they had internally. We at LinkedIn didn't have existing web pages internally. So the next step in the process was to pick a web crawler. And as every engineering team out there, you go through this sort of like a set of decisions that you want to make when picking a web crawler. Like, oh yeah, we can build our own. How difficult could it be? It's a web crawler, just a glorified, curl with a job on the side, and that's it. Web crawling done, right? You can use something that somebody else at LinkedIn is using, and we had other use cases, or you could go back to community and figure out what are the recommendations for this project. So there's, once again, you go to research community, there's going to be a survey paper, and you can read it and really get up to speed quickly on what this particular thing that you want to build is like. So there's a paper that talks about web wrapping, and circa 2010, it was like the state of the art of of crawlers at the time, not web wrapping, but crawlers at the time, right? And reading about what the state of the art is and what are all different concerns. So managing data, selecting the next set of pages to crawl, how to do this all efficiently and effectively, right? So all of this kind of made us reconsider building one on our own. We're like, okay, yeah, looks like a difficult problem. Probably don't want to spend all our resources just on this. There's actual project to deliver, a problem to solve. Somebody internally was using Scrappy. And Scrappy is sort of a framework that lets you automate like Python scripts that you use to actually extract structured data. But it's all written in Python, right? And the operated in Python. And the team had it, but they weren't really getting new use cases onto it. So that wasn't really an option for us. Now, and we were sort of looking for a particular set of things, right? We are mostly Java engineers. LinkedIn has a big Java deployment. I would say most of the engineers in Java, way more than 50% of engineers are Java engineers. We needed something that was open source, had a good license, right, an Apache license and something like this, and something that didn't require a lot of operational overhead, right? So the contestants were Heritrix, which is something that powers archive.org, Nutch, which is something that powers Common Crawl, and Bubbing, which is part of a law library. I think it's a library of algorithms for the web. And we went ahead and looked at them. So all three of these were, all three of these were Java projects, open sourced, different licenses, difference between like Apache and GL3, GNU version 3. So Heritrix doesn't have like a distributed mode. Heritrix you can run on one service, and you can kind of limit how that works. You can tell it you are only responsible for these domains, and then it will actually find pages that are not in those domains and kind of spill them into the file, and you can copy that file to the different machines that is responsible for domains. But that doesn't kind of come out of the box. It just exists. You need to operate it. You need to build it. Nutch is implemented in Java, open sourced. And is under Apache license, and it is implemented on top of Hadoop MapReduce. So if you already have a Hadoop MapReduce system in place, it's kind of a good choice to go after. And then Bubbing was the sort of like, it had distributed, it was really fast according to the research, but there wasn't a way to get at the source code. So the binary was available, but the source code wasn't. And to do it accomplished distributed coordination between the different crawlers using JGroups. And anybody ever use JGroups here? Or like JNI? It's like a framework for communicating between devices, Java, like circa 1998 or something. So it wasn't necessarily, from our perspective, wasn't like the freshest technology, so to speak. So we actually went ahead and installed each one of these, right? So Nutch and Heritrix we got up in a couple of hours and we were able to execute a crawl. Bubbing we gave up after a day or two. We couldn't configure all the different requirements that it needed to get it running on a machine. So I guess I already skipped this. The winner was Nutch, right? So it helped us with certain, so it's written in Java, so we were able to read and understand it, see the source code. It uses HDFS for storage, right? And we at LinkedIn have already a large deployment for Hadoop deployment, right? So HDFS is easily available. And we didn't need to worry about getting up machines or getting up reliable storage or replicating storage, none of that stuff, right? We can just put this data on HDFS and not worry about it. It allowed us to leverage existing infrastructure. It was proven to work by Common Crawl. They execute these massive crawls, billions and billions and billions of objects. So that's great. It means we would be able to scale it even if we needed to, even though we didn't need to initially. And we were able to orchestrate. So Nutch is basically a collection of jobs that work together, and we were able to orchestrate it with Azkaban. And Azkaban is a sort of Hadoop job scheduling tool that LinkedIn has open sourced. It's available for everybody. And the interesting bit of trivia is that Hadoop was actually refactored out of Nutch. So the folks that were building Nutch actually were building a MapReduce distributed file systems thing inside it. And people said, oh, well, besides Nutch, besides sort of building a general way to crawl the web, there's actually this really useful algorithm and this really useful implementation inside here. We'll pull it out and make that Hadoop, right? So that's the origins of Hadoop. So now the actual implementation of Satori, which is the project, the application of the use case for identity and having Nutch operating on HDFS. So this is our sort of general crawl flow, right? This is a diagram produced from Azkaban, just a job flow diagram. So this is built on Nutch 1.9, runs on Hadoop 2.3. We have this flow scheduled to run every 5 hours. That's actually a kind of an important thing to look at. You want to make sure that you want to crawl as often as possible. As much of your time as you can, you want to spend fetching data. That's going to be your sort of challenge, right? Because you need to respect robust.txt. You need to be able to make sure that you don't overload the system, right? So crawling is going to be slow. The default in Nutch, the default is like you fetch a page every 5 seconds, right? So only 12 pages per second. So you have this sort of, it takes a while to do it. We implemented, we were able to focus our crawl, so we really needed just publications. So we went out and found a bunch of sites that make publication data really easily available. And instead of trying to have a crawl that fills out a form for a particular topic, and then that goes ahead and gives us a bunch of URLs, we just iterated the URLs. We were able to see the pattern in the URLs, and you were able to enumerate all of them, and just take that and throw that at Nutch as a seed set of URLs and let it go to work on top of it. And we wanted to be sort of good stewards of the Hadoop cluster as well, right? So you imagine this is a very different workload than your other Hadoop workflow, right? None of the data is actually stored locally when you're doing fetching. You're actually going out on the internet and fetching all these documents. And when you fetch these documents, right, they have latency associated with them, way slower than disk local reads, right? This is going over the network, going out onto the public internet. Who knows what latency is there, right? So you want to be careful how you do it. And Nutch gives you some ways to tune how you perform these, right? First of all, it lets you control how many fetchers you have. Basically, you control the number of mappers that you allocate to this job, and that gives you sort of the number of machines that will be doing the fetching. And then on top of that, you can control how many threads you have running per machine. And one thread on that mapper basically maps to one site that you want to get data from. And that's how Nutch implements making sure that you respect robust.txt and you don't overwhelm a site. So you tune that, and you can also tune how many pages you try to fetch in one go. And then you can figure out when you want to cut off your fetch job. And here's also an interesting balancing act, because there will be sites that are really fast and they serve pages really quickly. And there will be sites that are really slow or slow you down with their crawl delay declaration in robust.txt. So you want to make sure that you fetch the fast ones as quickly as you can, but you don't have to wait for the slow ones to finish up. So the way we solve that problem, and the way Nutch lets you do, is just cut off the fetch job and say, OK, after n hours, just stop running this job. So the n hours we picked was 4 hours, and that allowed us to have like sort of 5-hour window between this job running and not interrupting itself. Okay. And one more thing that I want to note here, there are actually 2 different branches of Nutch. There's the 1.x branch and the 2.x branches. It's not like an upgrade. It's a replacement, basically. I mean, they came out from the same ideas, but they're actually very different implementations. And the 2.x branch, its advantage is you can use something other than HDFS for storage. We didn't really need that advantage, so we went with 1.9. But we did go ahead and output the results of our crawl in the same format as the Nutch 2.0 version does. So they have this schema called the web page. It's an arrow schema. We output the same arrow schema web page. So if we ever wanted to switch out the crawler for the new version, we'd be able to do it without impact to downstream calls. And at LinkedIn, everything is an Avro. Like everything that's stored in HDFS is an Avro format. So this kind of fit well with our existing tooling. So this is the extract flow, right? So once you've finished fetching, you want to go ahead and extract it. And this is where we apply our wrappers, right? And our wrappers represent the schema that we are putting the data in, right? So if we're outputting a publication. The output schema of this object that when we apply the wrapper to a page will be a publication. The way it also captures which page it applies to by doing URL pattern matching. So the wrapper that was designed for PubMed would say, this is a PubMed wrapper. I want to extract data from these URLs. And then we use XPath to sort of fill out the fields. So publication has an author, a title, an abstract, and we have an XPath selector to pick the data from the page from the field and pull that in. So that's our wrapper. And then initially when we first implemented, we had the fetch and the extract flow in one kind of giant flow, which was really nice because you never had to worry about when are you done processing all the pages you just fetched. You kind of just, it's when the flow completes, right? But the disadvantage of that is you were spending time on extracting data and indexing data that you could have been spending time on fetching data. And fetching is the sort of the long pole, right? Like that's the thing that's going to consume most of your time, most of your resources. So you want to do it. So we were able to split this up. And another advantage that this gave us, splitting them up this way, is that we were now able to re-implement or re-extract all the data without interrupting the fetch process. So we can continuously fetch without ever stopping that job and just keep going in the loops and re-executing the fetch flow. And then if we decided to change the schema for our wrappers, or we decided to change the schema for our output objects, whatever it is, right? We could just, in parallel, start rerunning the extraction job and go ahead and basically fix any mistakes or make any changes that we wanted to do without ever interrupting the fetch, which was actually, a great thing that we were able to do. And we wound up actually doing that a couple of times because, engineers change their minds, and sometimes you need to erase and rewrite. Another thing that we took care of is the way we indexed. At LinkedIn, we have Avro data, and we have this sort of format for every data that we have it indexed by the type of data it is, followed by the daily or hourly, and then sort of the year, month, day, or year, month, day, hour, right? So we indexed it the same way as well, and that enabled us to use all the other tooling that we have at LinkedIn for this kind of stuff. And the second thing we did is we prepended that with a host, right? So all our data is indexed by the domain, the web domain from which it's coming, followed by this timestamp. And that's important because if you ever need to delete the data because you got a, like cease and desist, or somehow you need to get rid of this data from your infrastructure, you can just delete the data from that host and not worry about affecting any of the other files, right? Versus if you had it one big blob, then you kind of have to write a job that would rewrite the entire blob, which is useful. Never had to use it, but we put it in place. So some lessons learned from here, and I kind of said it maybe 5 times already, but nonetheless. Crawl rate is bound by the number of sites and the site's crawl delay, right? So this is the thing that's going to be slow. For example, there was a site that we encountered that had a crawl delay of 30 seconds. So basically, you could fetch only 2 pages per minute, right? And we wanted to get 120,000 pages from there, so that would equate to 1,000 crawl hours just to get data from this one site. And typical crawl delay is about 5 seconds, so only 12 pages per minute, right? So it's really, really slow, right? We're talking about, usually we expect QPS in the thousands, but this is really slow. So you can increase crawl rate by just getting a bunch more sites, right? Like you find sites that have this data and just as many of them as you can, that's how you're going to increase your crawl rate. But there is also a problem. You're going to be bound by the type of data you're looking for, so not everybody has this data for you, and how constrained they are about the data, right? So ResearchGate actually doesn't let any robots onto its site, so you wouldn't be able to get ResearchGate to expand your data set. So there's another solution to this. You can bootstrap from bulk sources, right? So I mentioned Common Crawl before, great source of data. They have, they continuously do these crawls, and if you want to bootstrap a search engine, if you ever want to do that, Common Crawl will be a go-to place to go to get all that data. It's really useful. And to bootstrap, you can use Goblin, another open source framework by LinkedIn, which is really good at pulling. We use it a lot internally to pull our Kafka streams into HDFS or to pull out databases into HDFS, but you can definitely use it to pull data from external sites, and we do so as well. We used it to get data from Common Crawl and PubMed, which are available in bulk formats. And it pulls it right onto your HDFS storage, which is really nice if that's where you need it. Another thing is XPath extractors can get challenging on sites with rich data models. For example, for human, when you read a paper, you have the authors and you have a little suffix that shows their affiliation. So as a human, you understand, oh, this person must be affiliated with this university. But in HTML, it looks like two parallel arrays with the index being the index into the array. It's not at all clear how you'd figure that out with an XPath wrapper. Additionally, XML is great, but it's not always available. Some sites will explicitly not let you crawl their XML version of the document. And other sites, this is one really funny. It shows you things. It looks like XML, but if you look at it, actually escape XML. So it's just like, greater than, less than, ampersand signs all over the place. It looks really strange. Okay. And another thing that we learned kind of later on, but we did eventually learn it, is it's really easy to exceed Hadoop quota. So we are using, at LinkedIn, Hadoop is sort of leveraged infrastructure like everything else. So there are quota in place to make sure that you don't exceed it. You can definitely do it. Every fetch cycle produces a bunch of files. That's just part of how Nutch works. So you'll be generating a ton of files if you're doing a continuous fetch loop. So just remember to clean them up. There's a segment merge tool in Nutch that you can use to actually merge all the different segments into one bigger segment and behave better as a customer of this. OK, so now we got the data fetched, parsed, extracted, and indexed. Only the simple problem remains to match it to a member profile, right? So this is where our match authors, publications to members to power profile edit experience, right? So this is where the machine learning part of this comes in. The basic job is, here's this paper published on PLOS ONE by Charles. Here's his Charles profile. Match him. Figure out that this paper was published by Charles and ask Charles to go ahead and publish it to add it to his LinkedIn profile. And the overview of the system is kind of straightforward. This is what you would see in a typical production system. You have this flow. Once you've trained a model, you extract the feature vectors, you apply the model scores, and then you get this match data. You do it. The first part there is candidate selection is an interesting part. And then you can, once you've done that, you can actually, once you have the data on HDFS, you can sample that data to do training locally on your machine, right? So our data scientists were able to do the training part offline in R. So we started simple, right? It turns out that it's really useful when you can use global identifiers to match data. So publications sometimes have emails, and sometimes they have full names. LinkedIn has emails and full names. So the first model was really straightforward. You could do match by email precisely, and then that wasn't enough because the data kind of is dirty. So you could then do fuzzy name matching. And this shows that you had, I think, 0.83 precision just by email. But when you do email plus fuzzy name matching, and the algorithms didn't really matter how you did the fuzzy string matching, you got like 0.99, so really accurate, right? And the value of this is you can do this, right? And then you can get the matches really quickly, really well. And then you can actually put it in front of the people who are going to use this data and the members, and they can validate whether your idea and the matching is good. So first, you can validate that you're doing the right matching, you're finding the right people. Second, you can validate that you're actually doing the correct, that the product is useful, right? You can show it to the people, and they can say, oh, yeah, this is useful. I would like to add this to my profile. All right. So then next step was, so not everybody in a publication has an email, right? So a bunch of publications, not enough email. So that motivated the example of building a better matching algorithm that doesn't just rely on email. However, we were able to use the email matches to actually generate a data set of people who we knew we matched correctly. And then once we knew that the email match worked through validation from the members, we also knew that we could apply the email matching technique to the rest of our data to generate a training set for a more advanced model, right? So we're able to generate a training set of a couple 100,000 records from the data we had for the more advanced model. And then just trained a linear logistic regression to go ahead and do the implementation, do the matching using data from the profile. Now, the first thing that was kind of an interesting challenge to solve is any member could have published any paper. So you have 400 million members, 20 million papers. Now you multiply them, you have a huge data set to kind of try to do pairwise matching, right? So really neat trick. You use LSH, so locally sensitive hashing, by full name to match the publishers from the paper to the member profiles, and now you have a much smaller candidate set, like orders of magnitude smaller candidate set. Now this name disambiguation in academia is by itself a deep research topic. You can imagine most of digital libraries don't have full names. They have just first name and last name. So if your last name is Evteniev, not a lot of problem disambiguating. But if your last name is Smith or Lee or Shin, forget it. There's going to be a lot of common names to get rid of. So the logistic regression got us pretty far, and we were able to get 0.89 precision in recall, so a really good match to get the data down. And then there's some interesting features that came up that we used in our model. There was a lot of them, like a couple of hundred, so I won't list all of them, but some of them were interesting. So max name similarity was a strong indication of strong feature that we were able to use. Members in the medical industry, medical professional publish a lot, useful feature. Affiliation matching between members, so your affiliation on the paper and your LinkedIn profile data was a strong match. And highest degree is a PhD, strong match for research publication. Apparently, you have to publish a paper to become a PhD. And there were a few interesting features with negative coefficients as well. One of them is highest degree is an MBA. So apparently, to get an MBA, you don't have to publish research, or the opposite. And another one was that members in the banking industry. Apparently, if you're in the banking industry, you don't tend to publish your work. OK, so what's our current status? So after about 6 months of work, we were able to get, we have a bunch of publications we can still go after. So 56,000 publications pages with publications on them that we can still fetch, right? So a lot of data. We fetched 5,000, and a million of them are, there's a million, sorry. We fetched 5 million, and a million of them have gone. So 56 million still to crawl. Like I said, crawling is very slow, right? I would love for that line to be way down there, but. And then we also started crawling companies, right? We were able to apply our wrapper logic for publications, so lots of different sites, lots of different wrappers. But now we want to go to different domain. So for companies, we get addresses, location, name, that kind of stuff. So companies we just started, so only 2 million, and we targeted much tighter. So 2 million still left to go, and 2.5 million we already pulled the information for. And once we did, we applied to do the extraction, right? So extraction is also not perfect. We got 3.9 million publications extracted out of 5.3, and we just started doing extraction now on companies, so just not even a million yet. So some lessons learned from this. Target the data sources which have the data that you need, and you'd be really easy to get the data from, right? So get after those first. It will help you prove your use case, prove your ability to actually do it, prove out your tooling, prove out your operations. Add tracking to the entire flow, right? You want to figure out where you got this data from, how you were able to match it to this member, and what did the member say when you showed it to them, right? The entire flow. You want to get that done. It helps you, figure out how you're doing with the progress, helps you do some reporting on it, helps you feed back into the machine learning and training to be able to get a better algorithm. Do all of this offline if you can, right? The huge advantage that we had. Didn't need to worry about procuring storage nodes. Didn't need to worry about retention in Kafka or anything of that sort. And we were able to rerun our extraction over and over and over again every time we had a problem that we needed to fix. Really useful. And HDFS, of course, does replication for you and all that stuff, right? And then sort of get the product to the customers early, validate the process and the value proposition. Right? We sent this as an email test, and this was sort of one of the most successful marketing emails we ever sent out by conversion rate. So people actually read the email, then went to the page, and then clicked, yes, please add this to my profile automatically. Really useful. Most important, write it all down and share it with everybody. because that's how we can figure out how to build the next better system and how to leverage somebody else's work. That's it. Thank you. Sorry that I sped up there at the end.
We have a few minutes for questions.
Yeah.
How do you handle single-page applications where you can't get the HTML or the data by crawler?
Sure. So how do you handle single-page applications? Google recently published this protocol to let you share single-page applications as permalink, right? And they have, it's a hash bang. I think it's like an exclamation point and a hash sign, so bang hash. And when you see that, it actually expands out into a URL that you can hit the Ajax page. And most of the single-page applications that care about SEO, so basically anybody who you'd be able to access with a crawler anyway, implement that protocol to make sure that Google can get that data. So just to make sure you implement that protocol as well. There are some folks that use like a browser, like they pull up Phantom.js or something in the background and go ahead and do it that way. And I think Google is starting to use a Chrome browser to do it. So it might get more difficult in time, but for now, this works. Other questions? All right.
OK. Nicholas will be waiting in the Hunter room in case you have further questions. He'll be there for half hour, so you can ask him more questions in Hunter room. Thank you.
Thank you.